Okay, so this is Psych 222. It is Monday, February 22nd, and we are into chapter 5 of the book. Now, in chapter 5, we start talking about making inferences about population central values. Now, the key word here is the idea of making an inference. So, why are we making inferences? Well, let's just recap a little bit. We have a population right here, right? And the population has a whole bunch of observations in it. Maybe that's American citizens or anything we're looking at. Maybe people suffering from COVID-19, any kind of group that we're interested in knowing something about. Well, oftentimes on populations, we would like to know things like the population mean. So there's the population mean right there. So ideally, we'd like to calculate the population mean on that entire population, but the population is often very, very big, right? And we've talked about this principle before. Sometimes the population could be millions and millions of people. It could actually be an infinite number of coin flips. If we think about that in terms of a population, they're very, very big. So we cannot know this, right? We cannot know this definitively in most cases. Now, if your population is very small, and sometimes populations are small, then often you can simply just calculate the mean of the population and you actually know the parameter, right? This is the parameter we'd like to know something about. But since the population is usually big, we can't know it. So what we usually do is we want to get an estimate of it. And the sample mean will be used to estimate what's going on in the population. So we like to use the sample mean to estimate that population mean. Now, the sample mean, of course, is going to be based on lesser observations than the total population. So let's say our population here is based on 100, just as an example. Well, maybe our sample is based on 10 observations. So we know that when you base your estimate here using the sample mean, it's not going to be exactly equal to what you would get in the population. And the reason for that is because you're not gathering all the information. You're only gathering a sample of the information. So what this chapter is about is how to draw inferences about those population values, whether those population values are population means or other population values like medians, even variances. We would like to know how to make these inferences. Okay. The first thing we need to define here is the idea of a parameter. So the population parameters we typically deal with are the population mean, and that's what we talked about already. That's that mean of that population we're interested in studying. But as I mentioned, there's other population parameters that could be the population variance we'd like to know something about, right? It could also be the population median or a whole bunch of other different parameters. But remember that when we're talking about a parameter, we're talking about that characteristic of the population. Well, this idea of estimation and hypothesis testing, these are the tools we're going to use to get to know something about our parameters. Okay, so the idea of estimation means that we will get an estimate of the value of the population parameter of interest. Or we could also test a hypothesis about the value of the parameter. So I'm going to come up with my own examples here, and you can read along in the book to see what their examples are. But let's take the example of IQ again. Okay, it's a nice convenient example. Let's say that we're interested in estimating the IQ of Montanans. Okay, the IQ of Montanans. Well, the state has a lot of people in it, right? And there's a lot of adults in Montana that we'd like to know the intelligence of. So the state is too big to gather everybody's IQ. So what you'd like to do is get a sample. So when you take that sample, and again, maybe you base the sample on, I don't know, say 500 or so, you get the sample and you calculate the sample mean, IQ, and you're using that to estimate that population figure. Okay, that population IQ. That's what we mean by the process of estimation here. Now, the idea of hypothesis testing is sometimes we'd like to evaluate a hypothesis regarding some parameter, okay? So let's assume for a minute that the average intelligence of a normally healthy adult is equal to 100, okay? So if I have a population of normally healthy adults, intelligence-wise, that their population average should be about 100. Well, what I might be interested in doing is taking that sample of Montanans and seeing if I could argue that Montanans are greater or less than in terms of intelligence. So let's imagine for a second that we think that Montanans are very, very smart. Okay, Montanans are very smart. So if the average intelligence is equal to 100 in the country, well, maybe we think that Montanans will have a higher intelligence. So we might think that Montanans are not of average intelligence. Montanans will have a greater intelligence than 100. So when we gather our sample mean, maybe our sample mean is equal to 130, right? If our sample mean is equal to 130, then we'd like to evaluate a hypothesis. And the hypothesis is that Montanans are of normal IQ. Well, this might suggest that Montanans are not of normal IQ because they score so much higher than the population mean. Now, what I've just done there is not an official hypothesis test because there's more that we're going to need to develop, but this is the main idea here. If Montanans score 130 on that sample, right? Remember, that's just a sample of IQ. What does that tell us about whether they might be equal or not to the parameter here of 100? You know, if we got, say, 101, right? If this was our mean instead, well, this mean is very, very close to the population mean. So we might reason, even without knowing any more procedures, we might reason that 101 is close enough to the actual population average that this probably does not suggest that Montanans are of greater intelligence, right? Because 101, maybe that just occurred by chance, right? Even if the true average IQ of Montanans is equal to 100, it's possible to get a sample IQ of 101, right? That seems reasonable. But if their IQ came out to be 130, that might suggest that maybe there's something going on here, right? Maybe this is indicating that maybe the 130 is indicating that Montanans do have a higher IQ than average. So we see the idea here and why we're going to need that idea of sampling distribution of the mean that we talked about in the previous chapter. Remember in the previous chapter we said we've looked at some things that we're going to be putting into motion pretty soon. Well, we're going to start putting those tools into motion and using the idea of probability here. So I'm going to just draw a normal distribution that's approximately normal, and I'm going to put mean is equal to 100. Well, if the average in our sample for IQ is equal to that 130, well, where does 130 fall along here? Does it fall out here? Does it fall out here? Well, we don't know until we calculate that standard error of the mean, right? We need that standard error of the mean to tell us where 130 falls. So we need to develop that principle as well. And we've talked a little bit about that in the previous chapter. That's where we're headed with that, with doing a hypothesis test to answer a question like this on IQ. Okay, so a couple things here. Estimation, we want estimation, and then we want the statistical test. So estimation here, in their example, they're talking about anxiety ratings. Again, you can think of this in terms of IQ or anything you like, but they're trying to see here, does information from the sample, can it be used to estimate the mean decrease in anxiety ratings for the set of all anxious patients who may conceivably be treated with the drug. So they're giving people a drug to try to reduce anxiety, and they're trying to see, can they actually make a conclusion of whether that drug is effective? Well, the statistical test will be the information from the sample can be used to determine whether the population mean decrease in anxiety ratings is greater than 0. This example here, if the anxiety decrease is equal to 0, well, then that drug doesn't seem to be working, right? But they're trying to use a statistical test to try to see if the anxiety decrease is going to be greater than 0. So that again forms that idea of that hypothesis test. This is an analogous idea that they talk about here in terms of relating it to my IQ example. It's the same idea, because in their example, they're trying to see if there is a decrease in anxiety ratings. In our example, with the IQ, we're trying to see if there was an increase in IQ over 100. You see, the examples are very similar. So again, as I develop examples in the margins here, read through their examples and you can relate it back to what we're talking about, okay? Okay, so another one here, percentage of calories from fat. They want to estimate things, right? They want to do an estimate of how many calories are coming from fat and a whole bunch of other things. Nutritionally, we can do that, right? If you want to know, let me just use another example here. If you want to have an idea of how much fat does the population intake in their diet, well, maybe you take a sample of individuals and you analyze their nutritional patterns, right? So maybe you figure that on average, people take in, say, 10% of fat. Well, if you kind of set this as the benchmark and then you gather a sample and you find in the sample, let's say it's 30% in the sample, right? You find that there's 30% fat in the sample. Well, that suggests that maybe the actual true percentage is not equal to 10%. It would actually be closer to maybe 30%. So you see, what we're trying to do is we're gathering sample information to address something in the population. We're trying to get an estimate of what's going on in the population. Okay. So estimation of mu. Now, why are we focusing on mu? Well, again, remember, mu is the population mean. And why are we so concerned about averages, right? What is it about average that are so interesting? Well, we often want to compute averages for the reason that, remember, averages are very sensitive to scores, right, in the distribution. So if this is an average of 100, and this is, say, 105 over here and 115 over here, if I changed this score to 117, well, then the average goes up just a little bit. They're very sensitive. So a lot of what we do in research is we calculate averages. So it makes good sense that we want to get an estimate of the average, whether it's the average IQ, whether it's the average amount of fat in people's diet, whether it's the average recovery rate from COVID-19 or other metrics. Averages are really important. So we want to be able to study the average and estimate it really, really well. Well, let's look at this figure right here. Now, this figure is the sampling distribution for the mean. Now, remember what the sampling distribution of the mean is about. Remember from chapter 4, we said that if you have a population, right, if you have a population with a given mean, we are interested in knowing what the distribution of sample means looks like from that population. So just to recap our example, if I have that average IQ is equal to 100 in the population, we said that the mean of all the means you could gather from that population is equal to the mean IQ, right? We said that if you continuously sampled from this population, right, there's a whole bunch of population scores here. These are individual scores in the population. If you continuously sampled means from that population, well, the average of all of those means would be equal to the mean, which in this case is equal to 100. So that's what that average looks like. But then we also want to know what was one standard deviation of that distribution. And we said that one standard deviation of that distribution was sigma over square root of n. And that standard deviation of the sampling distribution, we said, is the standard error of that statistic we're computing. So this was going to be one standard error away from the mean. This was going to be 2 standard errors. This was going to be 3, etc. This is what this is showing right here. So this is summarizing a little bit of what we talked about last chapter. There's the average. And what this is showing is 95% of the means lie in this particular interval. So if we take the average plus 1.96 times, there's our standard error right there, right? That's this thing right here that I just computed right here. There it is. So the mean plus 1.96 of a standard error, or I go the other side, mean minus 1.96 times the standard error. Well, 95% of cases of those means lie in this interval. Now, why is that helpful? Well, that's helpful because that gives us an idea of where most of these means are going to fall, right? So if I sample means from that population and I have some normalcy going on here through the central limit theorem, remember the central limit theorem tells us this distribution will be normal for sufficiently large sample size, right? The size of my sample, if it's sufficiently large, then this distribution is going to be normal. Well, then I know where 95% of cases will lie. Now, one more detail here is where does this 1.96 come from? Well, the 1.96 comes from the z distribution. So remember the z distribution at the back of the book, that's telling you the different areas under the curve. Remember we talked, that's actually a calculus concept. It's telling you what's the area in this section of the curve, what's the area in this section of the curve. Well, when you look at the back of the book, you'll find that that 1.96 is going to divide up 2.5% here and 2.5% here. 2.5% and 2.5% is 5%, and that's why we're getting the balance of the 95% right here. So that's where that 1.96 comes from. It's coming from that z distribution. Okay, so we have a sampling distribution for the mean. Well, let's relate it back to our example again. Our example was with the IQ. So if I do this and say that the average IQ is 100, and we take our 130, right? The Montanans got 130. So they're somewhere over here. We're not quite sure yet where they are because we don't know the value of the standard error, but we know they're probably pretty far off over there in the tail. Then we might want to know, does that 130, is it far enough that it falls in this area of the curve, right? So, you know, remember we got our sample IQ of 130. Well, if the average IQ in the population is 100, and our 130 average falls in this area of the curve, that would suggest that that 130 is not a very likely result if it actually came from a distribution of normal IQ, right? So we see that we have normal IQ here is 100, and we're trying to compare the value of the IQ that we get based on our sample to that distribution of means. And I think it's fair to say that if that 130 is extreme, right, if it falls over here, what would we be likely to conclude? Right, we'd be likely to conclude that it looks like Montanans are more intelligent than average because their sample mean here is so extreme in the tail that at some point we're going to conclude that maybe their average IQ is not 100. Their average IQ is higher than 100. I mean, likewise, if it happened on this side, because this is the minus, right? So let's say instead of 130, let's say they got 70. Well, 70 is a lot less than 100. So maybe it falls around over here. Well, same idea there. We might say, well, it looks like Montanans are not of average intelligence, but on the opposite end, because that's showing a lower IQ. So we see this idea of why this 95% figure is important, and this whole kind of concept of how we're going to use this distribution, this sampling distribution, to help us make decisions on hypotheses. Okay. Again, I want to stress right now, you'll notice that we don't know the value of this yet, right? We don't know the value of that standard error, and that's going to make a big difference, right? Because if the standard error is a very, very small number, then 130 is going to lie off way over here. But if the standard error is a big number, right? Imagine if the standard error were equal to 30 points. Well, if the standard error is equal to 30 points, then what is one standard error away? 130, right? If that value of that standard error were equal to 30, then even if those Montanans got 130 in our sample, they're still pretty much in the curve here, right? They're not extreme like if it was over here. So notice the value of the standard error that we're going to compute is going to play a big role in how extreme our mean is relative to the population mean. So again, if one standard error is 130, well, we probably wouldn't say this is very unlikely, right? This probably would not give us reason to suspect that Montanans are of greater intelligence than average, because the standard error is 30. So they lie within kind of that normal part of the distribution. What we're really looking for are extreme values in the curve. Okay, and we'll return to that concept when we look at hypothesis testing, but this is that overall picture of how we're going to use distributions like this. And that's really important to grasp. Okay, so this is the exact same idea as we've just been talking about just above. We see when the observed value lies in the interval contains the parameter mu. So again, there's our kind of cutoff area, and we're trying to see where our statistic is going to fall. So if our value falls over here, well, that's not in this area of the curve. So this is kind of like that 130 that I just did up above, only it's a little bit more extreme. But let's take the 130 over here. If our values are falling in this area within that 95%, then we're probably not going to say that we have evidence that Montanans are greater or lesser intelligence. But if it starts to fall in these areas of the curve, right, then we're going to start to think that Montanans maybe are of greater intelligence, or lesser if it's on this side. Okay. Again, big picture here of how we're using this distribution. Really, really important to grasp this idea that when we're going to do hypothesis testing and estimation, we're interested in what goes on in the center part of the distribution. And as scores get too extreme, that's where we start to think something might be up. Okay, so again, we'll return to that. The idea of an interval estimate, okay, the idea of an interval estimate and level of confidence and confidence coefficient relates this idea of a confidence interval. So let's develop this idea a little bit. First, when we want to estimate mu, okay, well, we said that we could use the sample mean to estimate mu, right? You can use the sample mean to estimate it. But the problem is that using the sample mean to estimate the population parameter, we're always going to be off, right? We're always going to be off. So even if the population parameter is equal to 100, our sample statistic is never going to equal exactly 100, right? So it's probably going to be around 100. Maybe it'll be like 102, something like that, maybe 95, but it'll probably never equal 100. So this estimate here and this one are almost guaranteed to not capture the population parameter. Let me give you the analogy here, a really, really useful analogy. There's your boyfriend, girlfriend, spouse, whoever, and when you get home, you want to give them a big hug, right? You want to give them a big hug. Well, if you keep your hands together, so there's your hands, and you keep them flat together. So put your hands together, right? Put your hands together. They're flat, one on top of one another. If you go to hug your spouse that way, you're not going to be able to hug them, right? Because your hands are together. So what do you do to make a hug? You take one hand, you bring it this way. You take another hand, you bring it this way, right? That's not a very good hand, but there's a hand, and there's a hand. In order to get an estimate here of what you're interested in, which is the parameter in this case, that's the metaphor, you have to widen, right? You have to widen your hands so that when you do go to hug your spouse, you're going to actually hug them because your hands are wide enough to encompass your spouse. But if it's too narrow, if you're too narrow, then you do not hug your spouse. This is the same idea behind what's called a confidence interval. A confidence interval is going to build a margin of error around the particular sample value. So let me just clean up this concept down here and say that if we want to estimate the population mean, this is always going to be off because this is like your hands together, right? So you're never going to be able to hit the population mean, right? So you're going to always be off a little bit. No matter how precise you try to be, you're always going to be off. Why? Because your estimate is like 99.87, and this is not going to equal 99.87. It's probably going to be something a little bit different. So this idea of using a point estimate to exactly get the population value is going to be a hopeless idea. So what do? You build a margin around, you open up your hands a little bit, right? So maybe we go +1 on this side, we go -1 on this side, and that builds a little bit of a hug so that you can actually encompass the population parameter. You can actually encompass the person you're trying to hug. Okay, that's the idea of a confidence interval. So when we compute confidence intervals, we are going to compute one confidence interval, but we're basing it on the idea that we're computing a lot of them. So when we say a 95% confidence interval, we mean that in 95% of samples on which we compute a confidence interval, 95% of those intervals are going to actually capture the population parameter. So to clarify what that means, in this particular example here, the actual mean here is equal to 27. Okay, the actual mean is equal to 27. What they've done here is compute a whole bunch of 95% intervals. Well, they're called 95% intervals because about 95% of these intervals should capture the actual population parameter. Well, let's look at one interval, this first one right over here. There's the lower limit of the interval. There's the upper limit, right? There's the lower limit of the hug. There's the upper limit of the hug. Hug is fairly wide. Does it encompass the value? Yes, it does. Because this hug is capturing the population parameter. So that interval got it, right? That interval captured the population parameter. That's not a surprise because we'd expect how many of those intervals to capture the population parameter? 95%. So it's not surprising that our first interval there captured it. We would expect 95% of them to capture the population parameter. Let's look at the next one. Can we see the next one right here? Does that one capture it? Yes, it does. That one also captures the population parameter. How about the next one? That one does as well. The next one does as well, and so on and so on. Look at all the intervals for which the population parameter is contained in the interval. Well, we get to one here, this one right here. That one doesn't, right? Notice this one, this interval right here, does not capture the population parameter. It fell just outside of it. So if I were to put this on a, there's my 27, that interval looks something like this. It did not capture the 27. 27 is on the outside of it. Well, did we expect something like that to happen? Yeah, we did, because 95% of intervals are expected to capture the parameter, but 5% are not, right? 5% of the time, we expect to not capture the parameter. So there's one interval that didn't catch it. Here, the next one, or a couple down here, this one didn't capture it either. And so on. We can go to another one here. This one didn't capture it. So we would expect, if we're computing 95% intervals, that about 5% do not capture it. And that's exactly what we're seeing in this simulation. Now, this is a simulation based on 50 intervals, so it's not going to be exactly at 95% usually. But with enough intervals, you'll see that it usually gets pretty close to that 95%. That's the idea of the confidence interval. So if I want to estimate the population average for IQ of Montanans, I'm going to compute an interval, and maybe that interval is, say, 95 to 105. If that's a 95% interval, then we can say that 95% of confidence intervals computed on our sample, and as we sample again and again and again, see, we have a whole bunch of different samples, 95% of those intervals will capture the actual true parameter. Remember, these are different samples. So each time we do this, we are gathering a sample and we're computing an interval. Now there's our interval right here. Here's another interval. Here's another interval based on those different samples. When I looked at this one here, I just started the opposite way. I started at sample 100. But if you want to do it in order, start with sample 0, sample 10, 20, 30. And as you go to the 100 here, you see that 95% of those intervals are capturing the parameter. That's the idea of the confidence interval. And just remember that just key to this again is you have to have those different samples, at least in theory. When we actually compute a confidence interval, we're not sampling a whole bunch of times. We're only sampling once, right? We're only gathering one sample. But in theory, 95% of those intervals will capture the parameter if we kept on sampling. That's why you see a whole bunch of samples here. Okay, that's the concept. Well, here they show the example for the one we just looked at for the 27 here. So we have our whole bunch of samples, 1 through 51, et cetera, et cetera. And there's the sample mean computed on that sample, and there's the lower limit of the interval, and there's the upper limit. And then they say here whether that contains the population mean. And in that case, it does. That's like saying one of our intervals up here is containing the population mean. And then you can go on to sample number 2, et cetera, et cetera. And you could actually match up these with what you're seeing in the table. And you'll see that you come across a few intervals, right, that do not cover it. There's one, there's another. How many of those should we expect to see? We should expect to see about 5%. But the rest should be covering it. Well, here's an example of using a confidence interval. So we have a courier company in New York that claims that its mean delivery time to any place in the city is less than 3 hours. So they think, well, they're a good courier company because they can deliver things in less than 3 hours, which would be pretty good, right? On average, right? So you imagine like it's Amazon. And Amazon has a courier company and it's UPS, let's say. And if they said that on average, their delivery time is less than 3 hours, that would be pretty good. So the Consumer Protection Agency decides to conduct a study to see if this claim is true, right? It's just like again, forget the Consumer Protection Agency. Imagine if you just wanted to find out, right? You wanted to find out. Well, you want to know how quickly does Amazon deliver what you've ordered. Well, if they said that the average delivery time was less than 3 hours, how would you evaluate that? Well, you can't look at all deliveries that Amazon does or UPS does, right? That would take too long. That would just take too long. So maybe you get a sample, right? Maybe you get a sample. So in this case, that's exactly what the agency did. They randomly select 50 deliveries and determine the mean delivery time to be 2.8 hours, right? So there is their sample statistic based on the 50 deliveries. Again, why aren't they looking at all deliveries? Well, all deliveries could be all deliveries from now until the end of time. Or even in their database, there may be so many deliveries to look at, they're only selecting 50 and they're trying to draw a conclusion based on those 50 deliveries. They compute the average to be 2.8 with a standard deviation of 0.6 hours. Okay, so the agency wants to estimate the mean delivery time. So what's the mean delivery time using a 95% confidence interval? So if the sample is 2.8, they don't really care about the sample. They want to know, what does that suggest about the average? You can see all of the ingredients of what we've talked about are present in this problem because the agency claims it's less than 3 hours, right? The agency claims this is less than 3, right? You could even put the less than if you want there, less than 3. Well, this is our sample information. So let's build a confidence interval to see whether this can help address this issue. I mean, let's look at it from a different point of view. Instead of 2.8, let's imagine their time was like 0.1 in the sample. Right? Imagine they're like really, really fast. Well, what would you start to think? You would start to think, I think we've got pretty good evidence that the average delivery time is less than 3, right? Why? Because our sample result is so extreme that, boy, we're not even close to 3 hours. Look at, like, we're hardly at 3 hours at all. Now, we still need to build a confidence interval, but you start to see how this is working, right? Because the sample result is so extreme, you start to think, boy, we're gonna justify their claim no problem. On the other side, take it to the other extreme. Let's say that in your sample, their average delivery time is 100 hours. What does that tell you about this? Doesn't tell us anything yet because we got to do the computation just the same, but you get the idea, right? You start to figure, boy, in my sample, if there's 100 hours, if it took them on average 100 hours to deliver the package, boy, their claim is probably going to be false. Now, what makes the problem interesting here is the sample has a value of 2.8. So that's pretty close to the population value, right? Then it becomes a little bit interesting. You know, what can we say? What does the 2.8 tell us about the 3? Now, at first glance, it may look like you can say that, well, 2.8 is less than 3, and it is less than 3. But there's a problem. You cannot simply draw the conclusion that the average delivery time is less, right? I'm going to repeat that. Simply because you obtained a sample of 2.8, you cannot automatically draw the conclusion that the average delivery time is less. Now, why not? Because that's based on your sample, right? That's based on a sample mean. That's not a population mean. If it were a population mean, right? If that were a population mean, if the 2.8 were a population mean, then you would be able to say for sure that the average time is less than 3. Because you would actually have the population parameter. But you don't have the population parameter, you have a sample statistic. That's why we're building this confidence interval. That point is very, very important to understand of why we are doing the confidence interval in the first place, because we don't have the population parameter. Okay, so they want to estimate the mean delivery time using a 95% confidence interval. Obtain this interval and then decide if the courier's company's claim appear to be reasonable. So there's our sample size of 50. Now they're using small n here, and we'll continue to use small n. Previously, I used the big N to denote the sample. Sometimes it differs from book to book a little bit, but I will get used to using this as well. We'll use the little n for the sample. So we said their mean is 2.8, standard deviation is 0.6. Sample size is relatively large, so we know our central limit theorem is going to come into play in terms of that normality of the sampling distribution. The approximate 95% confidence interval is then computed using the formula we looked at. The mean plus or minus 1.96. Why 1.96? Because that cuts off 2.5% here and 2.5% here. That's why it's a 95%, because this is all 95, right? That 1.96, those are the Z values. And again, you don't have to look that up at the back of the book for the problem. You just have to know that's where they're getting the 1.96 from. I just don't want that to be a mystery as to where they're getting that from. So the mean plus or minus 1.96 times the value of the standard error, right? The value of the standard error. So we don't have the population value. They're not giving us the population value. They're giving us the sample value of the standard deviation. So we're going to use S as an estimate of that population value. And here is our confidence interval. 2.8 plus or minus 1.96 standard deviation, right? We're using S equals 0.6 here over square root of 50, because that's our sample size. In other words, we have 2.8 plus or minus 0.166 when we compute 0.6 over square root of 50. So the interval from 2.634 to 2.966 forms a 95% confidence interval for the mean delivery time. In other words, we are 95% confident that the average delivery time lies between 2.634 and 2.966 hours. Now, think about that for a second. We have just determined with 95% confidence that the average delivery time is between 2.6 and 2.9. What does that tell us about the courier company's claim? Remember, they wanted to argue that it's less than 3 hours, right? Well, we've just computed that 95% interval, and that 95% interval does not include 3. 3 is just up here, right? It's just on the outside. So 2.634 to 2.966, 3 is just above it. So therefore, we are within our bounds of that 95%, where 3 lies just on the outside of it. And that's why they're saying we can conclude that the data strongly support the courier's claim, because the limits we computed do not contain that value of 3. So in 95%, we are 95% confident that the average delivery time lies between these two values. So therefore, yeah, looks like they're right, right? Looks like they're right that their time of delivery is less than 3 hours. Now, let's imagine for a second that that wasn't what happened. Let's imagine that the actual limits were 2.5 to 3.5. Well, had the limits come out to be this way, right? If our 95% interval came out to be this, well, 3.0 is right in the interval. So had these been our limits, that would not have given us evidence to think that it's not equal to 3. But because 3 falls on the outside of the interval, that gives us some evidence to say that maybe that company has a point. So you see the process of how we're using that confidence interval to help us answer a question that the courier company is claiming. And again, juxtapose that example to what if we got something like this, and it makes sense when you compare the two situations. We could also loosely say that, you know, if we were to sample again from that population, we'd probably get a value between 2.6 and 2.9, right? So, you know, if we were to repeat the sampling, we'd probably get another mean value between there. So 3 definitely does seem to be on the outside of that interval. Okay. So there's the idea of a confidence interval, and we've developed this example in some detail, and that's a good example to kind of generalize what we've been talking about. And I encourage you, as you're going through the book and what we're talking about, spend a lot of time focusing on these examples that we develop in detail, because everything that we've talking about in here is summarizing what we've talked about so far today. So if something in here isn't clear, then you're kind of retreating back in the chapter to kind of fill in those gaps, but always aim for those problems and those questions that kind of unify everything a little bit. And that's what assignment questions try to do as well. Okay, let's stop for today. On Wednesday, we will discuss a little bit more about the confidence interval and a little bit more of those standard errors. And then we will continue on with chapter 5. So that's it for today.